NASA lost an asteroid. Not misplaced, not temporarily out of range. Lost, as in they saw it for exactly 1.2 days, tracked it, logged it, and then it disappeared into deep space and has never been found again. That was in 2007. The asteroid is still out there, its path is still unknown, and NASA's own impact monitoring system currently lists 89 separate windows between now and 2119 where this rock's unknown trajectory could intersect with Earth. Not one possible collision. 89. And scientists cannot rule a single one of them out because they cannot find the asteroid to measure where it is actually going. By the end of this video, you're going to understand exactly what it means for a space rock to be classified as lost. Not just absent from telescope view, structurally, mathematically unrecoverable with current data. You're going to understand why the 89 impact windows are not a number born from certainty. They are born from the opposite of certainty, from an orbital uncertainty so large it swallows decades of future space. You are going to understand what 340 meters actually does when it hits Earth. Not an abstract energy figure, a physical sequence, a before and after. And you are going to understand something almost no coverage has addressed. The reason that even with the most advanced telescopes on the planet, recovering this specific asteroid may be effectively impossible until it decides to show up again on its own. There is one more thing. The closest calculated impact window is not in the distant future. Stay with this. The asteroid is called 2007 FT3. It was discovered on the 20th of March 2007 by the Catalina Sky Survey, an automated telescope program in Arizona designed specifically to sweep the sky for near-Earth objects. The survey caught it in its field of view during routine scanning. Observers tracked it for 1.2 days. That is not a rounding error. That is the entire observational record. 1.2 days of data collected, then the asteroid moved out of observable range and was never recovered. 1.2 days sounds like enough. It is not. Calculating a reliable orbit requires observations spread across multiple weeks, ideally multiple months, to constrain the arc of the trajectory with enough precision to project where the object will be years into the future. 1.2 days of data gives you a fragment of an arc. From that fragment, you can derive a family of possible orbits, dozens, hundreds of mathematically valid trajectories that all fit the limited observations equally well. That family of possible orbits is the problem. Each member of that family traces a slightly different path through the solar system. Some of those paths miss Earth by millions of kilometers. Some of them do not miss at all. NASA's Sentry system, the automated impact monitoring tool at the Jet Propulsion Laboratory, calculates every possible trajectory consistent with the observational data and checks each one for Earth intersections. For 2007 FT3, Sentry found 89 such intersections across a timeline, stretching from now to 2119. 89 dates where at least one member of the orbit family would send this rock directly into Earth's path. The probability assigned to any individual window is small. The highest single event probability is approximately 1 in 10 million for a window in 2030. 1 in 10 million sounds dismissible until you understand what that number actually represents. That probability is not low because the asteroid is safe. It is low because the uncertainty is enormous. Scientists are not saying this asteroid probably will not hit Earth. They are saying they cannot calculate its actual position with enough precision to rule out impact entirely. If they found the asteroid tomorrow and measured its real orbit, that 1 in 10 million figure would change. It might drop to 0, or it might become something far more alarming. The uncertainty itself is the threat. And that uncertainty has been growing every year since 2007. Stay with this, because the size of this object is the detail that makes the uncertainty unbearable. 2007 FT3 is estimated to be between 270 and 590 meters in diameter. That range exists because the object was only observed for 1.2 days, and its reflectivity, the amount of sunlight it bounces back, has never been precisely measured. At the lower end, 270 meters, this is already a civilization-altering impactor. At the upper end, 590 meters, it crosses into a category that planetary scientists describe with very specific language. An object this size striking Earth releases energy equivalent to 2.6 billion tons of TNT. That is the equivalent of every nuclear weapon ever built by every nation in history detonating simultaneously at a single point. This is not a city killer. The class of object that destroys a city is typically under 100 meters. 2007 FT3 is not in that class. It is in the class that ends regions, that collapses ecosystems across hemispheres, that rewrites the climate for years afterward. The Tunguska event of 1908, a rock estimated at between 50 and 80 meters that exploded in the atmosphere over Siberia, flattened 2,000 square kilometers of forest. 2007 FT3 is 3 to 7 times larger in diameter. Impact energy scales with the cube of the size. Here is what the impact sequence actually looks like at this scale. The object enters the atmosphere traveling at roughly 20 kilometers per second. The atmosphere does not stop it, it slows it marginally, heats it to incandescence, and the pressure wave from its passage alone begins destroying structures before the object reaches the ground. If it strikes land, the crater is approximately 5 to 8 kilometers across. The blast wave propagates outward at supersonic speed for hundreds of kilometers. The thermal pulse ignites fires across a radius that dwarfs any city. Ejecta re-enters the atmosphere and creates secondary ignition across a radius measured in thousands of kilometers. If it strikes ocean, which covers 70% of Earth's surface, the energy transfer to water generates a tsunami sequence that does not behave like a seismic tsunami. It is larger, faster, and radiates outward in every direction from the impact point simultaneously. None of this is speculation. These are the outputs of impact physics models calibrated against the geological record of past impacts. The physics is not in question. The only question is whether 2007 FT3 ever gets close enough to use it. And here's the piece that should stop you. There's a 2030 impact window, less than 4 years away, and the asteroid has not been seen since 2007. The 2030 window carries a 1 in 10 million probability. But consider what it took to get to that number. Sentry ran the calculations across hundreds of possible orbits. It identified a subset of those orbits where the trajectory passes close enough to Earth in 2030 for an impact to be geometrically possible. 1 in 10 million represents the fraction of the total orbit probability space that lands in Earth-crossing territory for that specific date. The reason the number stays at 1 in 10 million and does not drop further is that there is no new data. To reduce the probability, you need new observations. New observations require finding the asteroid, and finding the asteroid requires knowing approximately where to look. That is the loop that cannot be closed. The observation arc is so short that the search area, the volume of space where 2007 FT3 could plausibly be right now, is not a point. It is not a region. It is an enormous three-dimensional cloud of uncertainty that has been expanding outward every year since 2007. Targeted recovery has been attempted. Astronomers have pointed telescopes at the most probable positions predicted by the orbital models and found nothing, not because the asteroid is not there, because the search area is larger than any telescope's field of view can meaningfully cover. The official classification in NASA's small body database includes a specific phrase that most coverage has not highlighted. 2007 FT3 is described as an object that cannot be recovered with targeted observations and awaits serendipitous survey observations. Serendipitous. That is the scientific community's word for. We are waiting for it to show up on its own. The recovery strategy for a potentially civilization-threatening asteroid is to hope a routine sky survey catches it again by chance. This is not negligence. It is the mathematical reality of a 1.2-day observation arc, degraded across nearly 2 decades of time. The orbital uncertainty has grown to the point where targeted searching is statistically no better than scanning the full sky. By the way, this is the detail that rewards staying this far. 2007 FT3 is not unique in its category. There are currently over 1,000 asteroids in NASA's impact risk table with non-zero collision probabilities. 2007 FT3 is unusual because of the combination of its size, its number of impact windows, and the irreducibility of its orbital uncertainty. Most objects on that list have enough observational data that the probability is trending towards zero as more data comes in. For 2007 FT3, the trend line is flat. It has been flat since 2007. It will remain flat until someone finds it. In 2012, a different asteroid passed within 60,000 kilometers of Earth, inside the orbit of the Moon. It was discovered 15 hours before closest approach. 15 hours. For a small object, that is sufficient. No action is needed. But the detection timeline is not irrelevant. It demonstrates something specific about the current state of planetary defense. The survey infrastructure is still incomplete. The telescope most directly designed to address this gap is NASA's NEO Surveyor, a space-based infrared observatory specifically built to detect and characterize near-Earth objects, including lost ones with degraded orbit solutions. It was built for objects exactly like 2007 FT3. NEO Surveyor has not yet launched. It has faced repeated funding delays and schedule revisions that have pushed its operational date further into the future, while the 2030 impact window for 2007 FT3 continues to approach. Ground-based survey programs like the Catalina Sky Survey, Pan-STARRS, and the upcoming Vera C. Rubin Observatory are finding new near-Earth objects every single week. Rubin, when fully operational, is projected to catalog more near-Earth asteroids in its first year than in the entire history of asteroid observation combined. But recovering a lost object with only 1.2 days of data from 2007 is a different challenge than discovering new objects. New discovery programs find things never previously seen. Recovery programs need to find something specific inside a search volume that is enormous and still growing. Rubin may find it serendipitously. NEO Surveyor, once launched, may detect it in infrared, or 2007 FT3 may pass through the 2030 window, then the subsequent windows, without ever being recovered, because the survey infrastructure that should have closed this gap is still not fully in place. Here is what every open thread in this video closes down to. The threat from 2007 FT3 is not primarily the probability number. The threat is what the probability number represents. A 1 in 10 million figure for 2030 is not a statement about safety. It is a statement about ignorance. Scientists are not saying this asteroid is almost certainly going to miss Earth. They are saying they have so little information about where it actually is that they cannot calculate a safe answer. That distinction matters because the probability does not behave like normal risk. For most hazards, more time means more data and smaller uncertainty. For 2007 FT3, more time without observation means larger uncertainty and no improvement in the risk calculation whatsoever. The 89 impact windows are not 89 separate dangers, each individually improbable. They are 89 places in the future, where the same unknown object's unknown path might intersect with Earth, and the list will not shrink until the asteroid is found. This is the part that the headline probability never communicates. 1 in 10 million for 2030 sounds manageable. 1 in 10 million across 89 windows for an object that has been unfindable for nearly 20 years against a backdrop of incomplete detection infrastructure. That is a different framing entirely. 2007 FT3 is a known unknown. An object that was found, cataloged, assigned a risk table entry, and then became unfindable, and has stayed unfindable for 2 decades while the impact windows accumulate. The 2030 window will arrive. The probability will not change unless the asteroid is found. NEO Surveyor, if launched, increases the chance of recovery. Rubin Observatory increases the chance of serendipitous rediscovery. Neither is guaranteed. What 2007 FT3 actually represents is not a prediction. It is a diagnostic. It shows exactly where the planetary defense architecture has a gap, not in the ability to detect new threats, but in the ability to close the loop on known threats that slipped through the observational window before the infrastructure was ready. The asteroid is out there right now, moving, crossing the same interplanetary space it has crossed every orbit since before humans existed. It does not know it is lost. It does not know there's a table with 89 entries and a NASA database with its name attached. It will either be found, or it will pass through every window on that list undetected. And the 89 entries will eventually expire into the past one by one. Not because the risk was resolved, but because the windows closed without incident. Or it will not. The physics does not negotiate. If this changed the way you think about what planetary defense actually means, not as a future problem, but as a present tense infrastructure gap with a specific name attached to it, share this video. Subscribe to be here when the next window opens.